Welcome to part 2 of this unit, in which we are studying about the basics of DC machines. In the last lecture, we studied about the working principle of a DC motor. In this lecture, we shall discuss the working principle of a DC generator. Working of a DC generator is based on the principle that if a conductor moves in a magnetic field, then an EMF is induced in it. If there is a closed circuit, then an induced current will flow due to this EMF. Now, the direction of that induced current is given by Fleming's right-hand rule. As per this rule, if we stretch the thumb, first finger, and middle finger of our right hand in a manner that they are all mutually perpendicular to each other, then the direction of thumb gives the direction of magnetic field. The first finger is directed towards the force, and the middle finger will give us the direction of current. So to explain the working principle of a DC generator, we will take help of a simple arrangement in which we have a horseshoe magnet, which is a permanent magnet, and that means that it has a north pole and a south pole. Now we place a coil inside this magnet which has a magnetic field in it such that the lines of force are from the north towards the south outside the magnet. So we have placed a coil inside this magnetic field, and the conductors of this coil are marked as A, B, and C, D. Now we give mechanical energy to this coil by rotating it with some means. That means is called a prime mover. For a thermal power plant, this mechanical energy comes from a steam turbine, whereas for a hydropower plant, this mechanical energy comes from a hydro turbine. So this coil is assumed to be rotating in a clockwise direction, and the force which is being experienced by this conductor AB is upwards, whereas the force being experienced by this conductor CD is downwards. So these conductors are moving in a magnetic field, and therefore an EMF will be induced in this coil, and if the circuit is closed with the help of a DC load to which we want to supply the electrical energy, then an electric current will flow in this coil. That electric current, the direction of that current in these conductors can be determined with the help of Fleming's right-hand rule. So let us see the direction of current for this conductor AB when we are seeing it from this point. So we see that the magnetic field is from right to left, the force is upwards, and now if we apply Fleming's right-hand rule, we find that for this plane, the current is going into it. Similarly, if we take the conductor CD, we see that the field is from left to right, the force is downwards, and now if we apply Fleming's right hand rule, we find that this current is coming out of this plane. So the current can be marked like this. It goes from A to B in the conductor AB, and it flows from D to C in the conductor CD. Here we should note that as of now, the conductor AB is under the south pole and conductor CD is under. And since this coil is rotating, the conductors will change their position, which means that this AB conductor will come under the north pole and CD conductor will come under the south pole. So let us see what happens to the direction of current when the conductors change their position. So here we have this conductor AB under the north pole. Direction of force remains the same, that is downwards. And here I have marked the magnetic field and force. So if we apply Fleming's right hand rule, we see that the current is such that it flows from B to A. Similarly, For the conductor CD, I have marked the direction of magnetic field and direction of force, and if we apply Fleming's right hand rule, we find that the current is such that it flows from C to D. So if we mark the current here in the coil, we see that the flow of current is like this, from C to D and from B to A. So under both the conditions, I have shown the direction of current when the coil and the conductors are have rotated. So here, when this conductor AB is under the south pole, the direction of current is from A to B. Whereas when this conductor is under the north pole, the direction of current is from B to A, which means that the current is not unidirectional. It keeps changing its direction. Again, when this conductor AB will come under the south pole, then the direction of current will be from A to B. So it flows like this, from A to B, then B to A, then again from A to B, then from B to A. So this current is basically an alternating current, whereas the load connected is such that it requires a unidirectional current. So here again, we need to inculcate a mechanism which can give a unidirectional current to the load, although the current inside this coil is alternating in nature. So that mechanism is known as commutator, which we had already seen when we discussed the working of a DC motor. So again, I'll explain the concept of a commutator. So we have taken this copper ring, we have cut it from the middle so that we have these two parts which are known as segments. So I have two segments here. This is the segment S1 and this is the segment S2. Now what we do is we again join these two segments but with the help of an insulation here, such that the current from segment S1 cannot go to S2 and vice versa. So this ring which we have made, which has segments separated from each other by insulation, is known as a commutator. This commutator is a rotating part. It rotates with the coil. So what we do here is that we have taken this commutator and we have connected this coil to these two segments. This is connected in such a manner that this conductor AB is connected to segment S1 and this conductor CD is connected to segment S2. When this coil rotates, this commutator also rotates with the coil. So the poles are here. I'm assuming a condition when AB is under the south pole and CD is under the north pole. So to collect this current which is flowing in the coil for a load, what we do is we take two brushes which are made of carbon. So I have marked them here as brush B1 and brush B2. These brushes are in contact with the commutator. These brushes are stationary. And here I connect the DC load. Remember that DC load means the direction of current should remain the same, although the current is alternating here in the coil. So here both the conditions are shown when this conductor AB is under the south pole and CD under the north pole, and with AB under the north pole and CD under the south pole. So in case 1, we had already seen that if the direction of rotation is clockwise and when the conductor AB is under the south pole, we saw that the direction of current will be from A to B, and in CD it will be from D to C. So this current will complete a path through the load which goes like this. So it comes here to the segment S2 and from here it goes to the brush B2 and then into the load, and it comes out of the load, goes to brush B1 and from there to segment S1, and from there it goes to the conductor AB in a direction A to B. So this is how the completion of this path takes place. Now due to this rotation, when the conductors change their position, so in conductor AB the direction of current now is from B to A. So let us see again how the current completes its path. So again here it goes from B to A, comes to segment S1, from S1 to B2, then enters into the load, then comes to B1, then segment S2, and then it flows through the conductor CD in a direction from C to D. So here we see that as the coil moves, the commutator moves with it, and in the first case, the brush B1 is in contact with segment S1, whereas in the second case, the brush B1 now is in contact with segment S2. So although the current inside the coil is alternating in nature, it periodically changes its direction, but outside this coil, that is for the load, the current remains unidirectional, and this happens because of this commutator. So the commutator here is acting like a mechanical rectifier, that is, it is converting this alternating current into direct current. So this is what happens when this coil is rotates and it gives electric energy to the DC load. So I explained the working of this DC generator with the help of this simple setup. So let us see some of the namings that we do for these parts. So generally, a permanent magnet is not used. We use an iron core and we magnetize it with the help of a DC current. So a winding is there where a current is flown and due to which a field is produced, and this winding is known as the field winding. The coil that I was showing is mounted on a shaft, and this is not actually a winding made of one coil, but it has multiple coils. So this winding is known as armature winding. And of course, this part we know well about it. This is a commutator. So in an actual generator, the construction is a bit different, which we will see in the next lecture. But these parts are the main parts of a DC generator. So in our next lecture, we will see the constructional features of DC machines, expression for induced EMF, the circuit model of a DC machine, the torque expression, and types and applications of DC machines.